Hi everyone, so today we're gonna look at how big are some of the really big numbers in BEAF. So BEAF is a very powerful notation, probably one of my favorite notation after studying it a little bit, and they are pretty mind-blowing for especially for beginners in Googleology. But let's get started. In this video I'm going to talk about 13 numbers in BEAF, basically from the smallest one to the biggest one. So the first one is the smallest, except like a few down, they're not in order, but in general they're in order. So this is the smallest one and that I'm going to talk about, which is called Tetratri, which is 3333 with four threes. And you can also write it this way and this way. And the interesting about BEAF is that you can write a number in multiple ways in BEAF. And you can also write it this way, 4 and 3. And this is actually the array of operator. So basically this is 4 array of 3. Basically it means there are four threes in here, pretty straightforward. So how big is this number? This number is already way bigger than Graham's number, which is around 36512 in BEAF. And it's also bigger than the chain arrow notation 3333. And this number is already much bigger than Graham's number. So this is similar to 33334 in the chain arrow notation, which is a 5-entry chain arrow. And in terms of the fast growing hierarchy is around f of omega square 3. So another way to look at how big this is, let's say t1 is 3, t2 is this number over here with three number of threes from the center to the to the last digit, or the last three, and t3 is this many threes with t2 number of t's from here to here. So pretty crazy already at t3. And I think T2 is already way bigger than Graham's number, just to let you know. And how big is this number? Tetratri is this thing over here. So T with T3 number of T's. So this is already way crazier than Graham's number. And this is just the smallest number I'm gonna talk about in this video. It's already pretty crazy from this on. And the second number I'm going to talk about is Pentatron, which is 3 with 5 threes. So obviously you can write it this way, 5 array of 3, or you can also write it this way. I want to point out that, the reason I brought up this number, actually I don't plan to talk about this because nothing's too special. But the thing is, this number is around approximately the same as Gutstein sequence. So the G16 in Gutstein sequence, which is pretty big, and also around the same as Federman's N5. So in terms of the fast growing hierarchy is around f of omega cube 3. And as you know, some of you know, N4 is used to be a lower bound for 3 3. So anyway, N3 is much bigger than N4, but this is not bigger than 3 3 yet. But still very big. So the third number is called this thing over here, duper try, which is something like this. So 3 try 1 2. So what it means is 3 3 3 3 3 3 3. So again, this is a linear array. So everything from we talk about so far is linear array. So the most beginning of the basic level of the BEAF. So in this array here, there are try number of threes. So try of course is sun tower 3 triple arrow 3. So this is already way crazier than this number over here. There are 3 triple arrow 3 number of threes over here, and we already know that just 4 threes is already way bigger than Graham's number. And you can also write it this way. However, I have to point out that this does not equal to this. You cannot write it this way. This is a much bigger number than this number, and I would talk about that a little bit in a moment. In terms of the fast growing hierarchy is f omega to the omega plus 1 2. So already a very big number. The reason it is not equal to this because this is a pentation array, way more powerful than this, and this is actually kind of ill-defined right now. But I will talk about that in a moment. So the next number, the fourth number is Latri. So what is it? It's 3 3 3 1 2, or you can write it this way. And in terms of the fast growing hierarchy, or actually f omega to omega plus 2 is this number over here. This one is f of omega to the omega plus 1 2. So it looks similar in terms of the fast growing hierarchy. But anyway, And this one you can see there's a, a 1 over here with parentheses. Here actually 1 it stands for, it means kind of mean like the x to the power of 1 structure, which means a row. And if it's a 0, it means x to the 0 structure, which is an entry. And x to the 2, it means a plane, and x to the 3, or or something like this, is a realm, and then 4x to the 4 is a fun, something like that. I'm not sure. So basically, the thing inside the parenthesis here, it kind of represent their dimension. So this is a 1 dimension. So a linear array would kind of consider a 0 dimension. This is 1 dimension. So if it's a 2, then it means it's a 2-dimension array or a dimensional array. So how big is this number? Is of course much bigger than this thing over here. So A1 is 3, A2 is 333, A3 is this many 3s with A2 number of 3s, and this number is equal to AA3. You can pause the video if you want if I talk too fast. It's pretty crazy already. And then I think this is kind of the limit for a linear array with this many entries. This is kind of, we're stepping into the dimensional array. So the next number is do try. So something like this. As you can see, 2 here, it means 2 dimensions. So this is a 2-dimensional array. And it's very difficult to try to picture what it looks like. So it occupies a 2-dimension. So not just a flat thing. It kind of means 2 planes. You can actually Google it yourself. There are some pictures online to show, kind of give you an idea of what it looks like. And maybe I'll try to put a picture on the thumbnail of this video. You can try to imagine what it looks like. So this one, you can write it this way: 3 square and 3, or 3 square array of 3. Of course, this, like I said, this does not equal to 9 and 3. You cannot solve this in this case if it's written in a power form. This is a much smaller number. This is just an array with 9 3s. This is much bigger than that. In terms of the fast growing hierarchy, is f of omega to omega q square 3. And I told you this already. And this is kind of like again, it's a 2-dimensional array. And so you need a plane to represent it. The next number is I'm not sure how to pronounce that. So it's something like this. And you can also write it this way. In terms of the fast growing hierarchy, is f of omega to the omega square 3. And you can see this is taking the form of a power tower. So this is kind of a smaller tetrational array already. And then the next one, number 7, is Gongulus, and this is famous for being one of the number used to define the big number oblivion. And it's written this way, and you can also write it this way: a Google n10, or a Google array of 10. This one doesn't mean that it has a 10 with 100 with a Google tens. This is not a linear array. This is a 100-dimensional array, or in order to represent it fully, you have to write it in terms or in the form of a centera, which is a 100-dimension cube. It's kind of hard to imagine. I mean, that's why math is way crazier than physics. I mean, people who say physics is crazier, I would say you're wrong. I mean, in physics, we're trying to find out if there's a 4th or 5th dimension, or what does it look like. In math, we're way beyond that already. We're not even trying to figure out what it looks like. We're already using it in math already. We're not even saying 4th, 5th, or 6th dimension. We're talking about 100 dimension, even Graham's number dimension, something like that. Anyway, as you know, tesseract is a 4-dimensional cube. So just give you an idea. And in terms of the fast growing hierarchy, this is f of omega to the omega 110. So pretty big. And then the next number is Kungulus, another number used to define oblivion. This is a much bigger number. It can be written this way, or you can write it this way. So as you can see, this is a pentational array, and at this point, BEAF is kind of ill-defined already. So BEAF is only well-defined up till tetrational array. So at this point, it's just assuming it's well-defined, and it has a in terms of the fast growing hierarchy, is around f of gamma 100, which is pretty big already. And then, I mean, all of them are big. And then the next one is Triaculus. Well, actually, this number is smaller than Congulus, but anyway, this is 3 and 3 and 3, or 3 array of 3 array of 3. You can write it this way, and which is equal to this. And again, this is a pentation array, but as you can see, this is smaller than this thing over here, but still very, very big. And it is, this is the fast going hierarchy. The next one is Stacus, or is also called the Big Mac, which is written this way, 10 10/2, which means it is 10 array of 10 array of 10, which has 10 10. So this is completely another level. And this is, at least according to the Google wiki, is already bigger than SCG13. And on the other hand, of course, much bigger than tree 3 already. Something this simple is already bigger than tree 3. And tree 3, as you know, is very, very crazy, unbelievably bigger than Graham's number. But however, using BEAF, you can write something this simple to beat it. However, it's ill-defined. But anyway, the next one is the Whopper, which is 10 100/2, which means something like that with 100 tens. And again, much bigger than SCG13. The next one is Big Boowa, which is something like this, 333/2. Again, much bigger than SCG13. How big is this number? If A1 is 3, A2 is 3 and 3 and 3, which is this number over here. I talk about that. And A3 is this thing over here with this number of 3s. Again, this is an unimaginably big number. And how big is Big Boa? Big Boa is AA3. You can pause the B video if you want. And the last number I'm going to talk in this video is the Great Big Boa. Is 334/2. How big is this number? If A1 is 3, which is, I just talked about that same thing. A2 is this thing, A3 is this thing with A2 number of 3s. Then the Great Big Boa is this thing over here. A with A3's number of A's. Pretty crazy, way beyond SCG already, but still smaller than Loader's number. Even the Mea Lokapua Umpa is still smaller than Loader's number. But anyway, this is just, at least this is one of the biggest number I can kind of explain in terms of BEAF. The Mea, that thing is hard to explain for that number at that point. But I think these are the, this is already in the Legional array, something like that. I forget what it's called. But anyway, this is at least even tetrational array is already very mind-blowing. Even the most basic form of BEAF already way beyond what you think. And still, even I'm sure this video doesn't give justice to BEAF. It's just way bigger than you think. If you think Graham's number is big, think again. I mean, it's true, Graham's number is big, but there are things that are way bigger. And I think, yeah, if people said this number is nothing or whatever, you just don't understand this number. And some people even say those they have used, those number have, or Graham's number have used in physics. I would say no. If you say yes, then you doesn't know the size of this number. You cannot even imagine, if you think Graham's number is big, so many up arrows, but this thing cannot even write it out in terms of linear array, because those things, the tetration array, it means you need tetrational space to represent, and I'm pretty sure no one can imagine what tetrational space is, let alone pentational space or whatever. Even the, I just told you the 100, the centera thing, 100 dimension thing. I mean, physics even nowhere near can think about what that means, but it's used in math. So anyway, this is the try to blow your mind a little bit with BEAF. So anyway, thanks for watching and have a nice day.